Okay, we are going to start chapter 3 today, which is all about physical science connections. The cool thing about this chapter is everything that you guys learn in this chapter we really use throughout the whole rest of the year. So I know you're always, presented with that impending question, when am I ever going to use this again? You're going to use it a lot the rest of the year. A lot of concepts in earth science, whether it's us talking about concepts that have to do with volcanoes or how weather happens, things like tornadoes and hurricanes, all have to do with the stuff that we talk about in this chapter. So we're going to talk about in 3.1 today, types of energy. And I know that's not a new word for you when you think about energy. I know we've all heard of it. You talk about, I got a lot of energy today, I don't got a lot of energy today. It's kind of on the right track, but remember in science class, we can get a little bit more specific than that. So chapter 3, physical science connections. So here is the scientific definition of what energy. Energy is the ability to create change in a system. So if you create change in a system, energy is involved. And because we are in earth science class, we focus on what does this have to do with earth. So we have heat energy on Earth's surface here. Where is that coming from? It's coming from the sun. So Earth's surface heat energy comes from the sun. We do get a little bit that comes from volcanoes and geysers, which if you don't know what a geyser is, those are those hot springs that are forcefully ejected up from the ground. But if you look at this little picture here, you can see sun's energy and how when it comes to the earth, kind of what happens to it all. So you can see as it comes in, 5% of it right off the bat, we estimate is scattered by the atmosphere. 3% gets absorbed by our atmosphere in a layer called the ozone layer. 17% is absorbed by atmospheric gases, water, vapor, and dust. 22% gets reflected back out by the clouds. And then now the stuff that's finally made it to the surface, 3% of it gets bounced back based on what it is hitting on Earth's surface. And then 50% of it actually gets absorbed by the surface of the Earth. So our heat energy here on Earth's surface actually comes from the sun. So the sun emits radiant energy that is mostly what we call visible light, but it also includes some other types of energy, infrared radiation, and then ultraviolet light. And we're not going to get into too great a detail with this. I'm going to show you a little video probably in class, but this is something called the electromagnetic spectrum. So this is showing us different types of energy. So when you look at this, some of these may look familiar to you, like radio waves, microwaves, and yeah, those things are familiar to us. One thing I just want you to notice here is you'll notice what we call the wavelength. So when you look at the wavelength, that's the space in between what we would either call two crests or two troughs. When you see kind of like the bumps on the top, that's what we call a crest in a wave. You'll notice as you go to the right side of the electromagnetic spectrum, they have a shorter wavelength. And you look at those things, gamma rays, X-rays, ultraviolet rays, all of those things should kind of sound a little bit familiar to you in terms of, if I go to the doctor and I get an X-ray, are they, taking special precautions so that the nurses aren't being exposed to those X-rays? Yes. When you talk about ultraviolet light, we talk about why we put on sunscreen. So the things on the right-hand side, those short wavelengths, we have shown to have increased risk of cancer over prolonged exposure periods. So the things on the right, the short wavelength, that's what we associate those things with. The things on the left-hand side have what we call a longer wavelength. So you'll notice in between those crests, they're much more spread out. So things like radio waves, microwaves, infrared, that's the heat one that we just talked about. And you can see in the middle there, that is what we see as human beings. We see visible light. So when you look outside and you see colors, that is visible light. So that is the only thing that we see is in the middle part there. And it's actually a little bit of a blessing because you can imagine if our eyes had the ability to see all of this other stuff, that would be a lot of information coming in at once. When you start to get into the field of astronomy, we talk about how we do have telescopes that pick up these other types of energy waves, X-ray telescopes, gamma ray telescopes, we have radio telescopes. So we do have all of these other things, but for us as human beings, we only pick up on that middle one there. So the stuff on the right-hand side, short wavelengths, those things can be damaging to humans if we're exposed to them over prolonged periods of time. Stuff on the left-hand side, those are our longer wavelengths. So Earth's surface heat comes from the sun, and Earth's internal heat energy mostly comes from its core. So we still have from when the Earth was forming early on, billions of years ago, we still have internal heat energy coming from essentially what the Earth was, this molten ball of rock, and it's just been cooling off over time. So just like anything else, just like when you take a chicken out of the oven, you take a casserole out of the oven, it's going to cool off from the outside in. Same thing with the Earth. So we do have internal heat, and that's coming from its core. So atoms are the smallest building blocks of matter. They can organize themselves into molecules, and we talk about them right now because they have a little bit to do with when we talk about energy and we talk about heat. So atoms are so small that 200,000 of them could fit across the thickness of a piece of aluminum foil. So think about just even how thin that is, and now imagine lining up 200,000 of them end to end. That is how small atoms are. So they are the smallest building block of all matter. So when we think about anything, think about water, think about you, think about a tree, think about your dog, all of those things, smallest building blocks of all of those are going to be atoms. So we have different types of energy. Depending upon what's happening, we have different names for them. Here's the first one, kinetic energy. So kinetic energy is the energy of motion. When you guys see that word kinetic, that means movement, motion. So if something is moving, it has kinetic energy. If you are moving, if you're walking, you have kinetic energy. If you take a baseball and you throw a baseball, it has kinetic energy. If we heat something up, it can have kinetic energy. So when we add energy to things, it makes those atoms move faster. So faster atoms have more kinetic energy than slower atoms. Now, one thing you got to remember about atoms, they are constantly moving. They never stop. So even if we're talking about a chair, if you're sitting in a chair right now, the atoms in that chair are moving. They're constantly moving. They never, ever stop. So we can get them to move faster by adding energy to them. We can get them to moving slower by taking energy away from them. But whatever the case is, it doesn't matter if we're talking about solids and liquids or gases. Those atoms are always moving. They never stop. So atoms have kinetic energy, the energy of motion. So imagine atoms were big enough to see. So if we look at this picture here, when we look at atoms and we talk about kinetic energy, they're not going to always all have the exact same amount. So some are going to have more, some are going to have less. So we use arrows a lot in physics to describe energy and motion. So obviously in the picture here down in the bottom, which atoms below have the most energy, it's going to be the ones that have the longest arrows in them. Now, if kinetic energy is the energy of motion, potential energy is what we call stored energy. And you may have heard of that before if someone says, you got a lot of potential. That just means you haven't used it yet, right? Same thing with energy. So potential energy, just haven't used the energy yet. There's a lot of different ways that we can give potential energy to objects. One of them is simply by taking an object and moving it above the ground. So height will actually give objects potential energy. Just by you even taking something, if you take your book, you take your iPad, you take your backpack, you lift it above the ground, you are giving it potential energy. So height gives objects potential energy. And think about that. The higher up you go, what do you think you're doing to that amount of potential energy? And I think we all know the higher up it goes, the more potential energy it's going to have. So if you look at this ball on the very top, it's going to have the highest amount of potential energy. He's going to push it. And what's happening is just simply a transfer of energy. We cannot create or destroy energy. It's something called the law of conservation of energy. I'll say that again. You cannot create or destroy energy. You're simply transferring it from one thing to another. So if I look at the ball at the top of the hill, it has potential energy. He pushes it. It is now being transferred to kinetic energy, and it has much higher kinetic energy as it's going down the hill until eventually it gets to the bottom. And think about what you did to potential energy again. You've dropped potential, you've increased kinetic. So it's just a transfer back and forth and back and forth. It's just like when you eat food. So we get energy from our food. When you are eating and consuming that food, you are just taking energy that's in the food and you are taking it to your body and you're using it in your body and then transferring it to something else. So we cannot create or destroy energy. So we like to use roller coasters a lot. We talk about transfer of energy from kinetic potential. At the top of a roller coaster hill, the car would have more height energy. So you can see the picture on the top here, really high potential energy, but low kinetic energy because it's not moving very fast, right? But it's up there really high. After that roller coaster gets moving and we have that energy transfer, near the bottom, I'm going to have low potential but high kinetic energy. So it's just simply a transfer of energy. Heat is also a form of energy, and as we all know, it can be transferred from one object to another. If you've accidentally burnt yourself before, And how energy likes to move in terms of heat, it likes to move from fast to slow. And that's the reason why you burn your hand, because the atoms in the pizza pan, or in this case, the spaghetti plate, are going to be moving much faster than the atoms that are in your cooler fingertip. So that energy transfer goes from the plate to your finger. Because think of it, if it was the other way around, would you burn your hand? No, you wouldn't. So fast to slow for heat transfer. Force that opposes the motion of two objects moving across each other is called friction. So anytime two surfaces rub against each other, we can have friction, and depending upon what the surfaces are like, the friction can be different. So you think about in sports applications, we have a lot of applications where we want friction in sports. If you're a basketball player, you want to have shoes that are sticking to the court so that you're not sliding all around. If you are in track, you want to make sure your cleats have spikes in them. If you're a cross-country runner, same thing. Football player, baseball player. We want to have friction. We want to have that so that we're not sliding around. I mean, can you imagine shooting a three-pointer in essentially socks? It's not the same thing, right? A little bit different. But now we also have other sports where we don't want friction. When you think about hockey players, think about swimmers, those are things where I don't want to have friction. So I'm going to do everything in my power to try to reduce that friction. I'm going to try to have my skates polished or sharpened. I'm going to have my if I'm a swimmer, I'm going to make sure I'm wearing a swimsuit that is going to reduce friction with my body. Maybe I'm going to wear a swim cap so my hair is not going through there. Swimmers will actually shave their whole body as well to reduce that friction with the water. So friction is a force that opposes the motion of two objects moving across each other, and as we know, it gets converted to heat. Living in northern Minnesota, if your hands are cold, you don't have mittens on, we know we rub them back and forth, and what happens? You feel that heat immediately. You are producing heat just by that friction. The end of the section kind of goes a little bit into energy in terms of us as humans and like how we use energy. So they talk a little bit about how energy can be wasted. So for most cars, only 20% of the gas burned by the engine is used to move the car. Obviously, this can be different depending upon which vehicle you're driving. But when you think about that, 80% of the energy in an average car is going to be wasted as heat, whereas 20% is going to be used towards motion. So when you think about that in terms of money, think about if I put, hypothetically speaking, $1 of gas in my car, only 20 cents of it actually went to move the car. 80 cents is wasted. So from an economic standpoint, not very good. And that's why if you're a person who has a car that is much better at doing this, so now if you start taking that 20% and increasing it to 30%, 40%, you're seeing that your car is going to go further for the amount of gas that you put in it. And if you're an engineer, that's what your job is to do. If you work for a car company, you're trying to make sure consumers have that raised up, because a lot of consumers care about that because they don't want to be spending that much on gasoline. Your book also talks a little bit about light energy. So light bulbs take electrical energy and transfer them into light energy. Now, the picture here is I'll call these old school incandescent light bulbs. So these are the ones that have a tungsten filament on the inside of them. You heat it up, you run electricity through it, the tungsten will actually glow. Very inefficient way to produce light energy. Only about 2% of it actually gets used. So if you want to use that money factor again, so imagine if I'm paying, $1, only 2 cents of it went to actually light the light bulb, and the other 98 cents is completely wasted as heat. These ones are the ones that feel hot to the touch. Only 98% of the energy is produced. Only 98%, or I should say this a different way, 98% of the energy produced is heat. 2% is actually light energy. So you can start to see how people are switching over to light bulbs that are much more efficient, like LED light bulbs. They are much, much better at, and I don't know the number right now off the top of my head, but you're talking almost a complete and total shift. So now you're using almost everything is turned into light energy and not heat energy. Finally, the last thing in the section, it talks about where we produce electricity in the United States, and that is primarily in what we call power plants. This is the most common way that electricity is produced. In the United States, our current number one ways that we produce electricity are by burning fossil fuels. So fossil fuels are called that because they are from the remains of ancient plants from millions and millions of years ago. So we take these things that are storing all of this energy like coal, oil, and natural gas, and essentially what we do is burn them. When we burn them, we release energy. Just like our process in our car where we lose heat at each step, the same thing has happened in a power plant. So every step along the line, I'm going to show you a picture here in a second, we're going to lose a little bit of heat. So typically what you're doing is you're burning coal, gas, or oil. So you burn it just like you do for a campfire, and that is going to create heat. They use that heat to heat up water. That water creates steam, and that steam turns what we call a turbine. So think of like a giant propeller for a boat. That's kind of what a turbine is. That turbine then, by using magnets and really other cool science stuff that we're not going to get into right now, in a generator produces electricity. So same thing, just like if you guys have a generator at maybe your cabin, or maybe you have a generator, you've seen someone use a generator before when they were camping. So usually we put gasoline in that. In this case, it's the same thing, burning something. We're just using coal, gas, or oil. That electricity is then sent to our house. Now, as you can see in the arrows here, the red arrows, everywhere along the way, we lose a little bit. So you lose heat energy everywhere along the way. So once again, if you're an engineer, you're trying to design, how can I reduce all of those red arrows, because then I'm going to get more bang for my buck if I am essentially a person producing electricity. So this is from 2019. This is U.S. primary energy consumption by energy source. So you can see right now our numbers have changed a little bit from what is in your book, because your book's getting to be a little bit old here now. So 37% petroleum or oil, then we have 32% natural gas, 11% coal, 8% nuclear. So coal is actually going down a little bit. Renewable energy is going up a little bit there, and then you can see in the renewable energy there, those are all of what we call renewable energy sources. So those sources, if managed properly, are not going to run out. They are things that the wind is going to keep blowing. Wood, if it's managed sustainably, we can grow forests and we can replant them, and we can grow them and we can replant them over. Solar, we have geothermal, which is energy that comes from the ground. Biomass waste, that's actually what they do in Hibbing here. One of the fuels that they will actually burn. So in a paper making process or in the logging industry, if they have waste wood, they can actually just burn that if they can't turn it into anything else. And then biofuels, those are kind of like a cool off branch. There's a lot of different things that can be. Biofuels would be fuels that come from life in some form. So, which can be wood as well. As you can see, that's in the same sort of a category there. So this is changing, and it's ever changing. It's extremely controversial. Fossil fuels, one of the things in the past that we're highly concerned with is they produce a lot of pollution. So looking at technology to reduce the amount of pollution that's going into the air. The other thing would be looking also at the future, is saying that these things eventually are going to run out. We don't have an infinite supply of fossil fuels. At some point in time, they will run out, whereas we look at our renewable energy sources, they will not run out. But there's a bit of a catch there. You can't just say, well, why don't we just switch over and start using renewable energy? It's much more complicated than that. Renewable energy currently is expensive. So if you were to have everyone just switch over to renewable energy right now, economically, would that be feasible? Could we actually do that? So it's really important to kind of look at a balance of trying to have a shift over, but not doing so in such a dramatic fashion. All right, so all about energy. So remember, energy, we cannot create or destroy energy. Also remember that energy is just the ability to create change in a system. If you're creating change in a system, energy is involved.